welcome to The Explainer. Today we're going on a bit of a journey to see exactly how cutting-edge AI agents are built to actually interact with the real world. We talk a lot about AI models generating text, but building a system that can independently use tools, navigate the web, and correct its own mistakes, yeah, that is a completely different ballgame.
Think about it for a second. Why does an AI that can literally pass the bar exam suddenly fail to book a simple flight? Well, generating intelligent-sounding text is vastly different from taking reliable, autonomous actions using external software tools. Answering a legal question, that just requires outputting the right sequence of words. But booking a flight, that means deciding to click a specific button, querying a database, parsing the response, and, figuring out what to do if the site crashes. To pull that off, the AI needs a very specific kind of training.
So here's our roadmap for today. First, beyond imitation learning. Second, the tool calling trio. Third, rewarding and training agents. Fourth, capability versus reliability. And finally, single versus multi-agent systems. Let's dive right in.
Section 1. Beyond imitation learning.
Okay, so before an agent can navigate complex tasks, it goes through Supervised Fine-Tuning, or SFT, which is essentially imitation learning. Think of SFT kind of like a student copying the teacher's homework, just to learn basic syntax. It teaches the AI the schema literacy, what a JSON file looks like, or the basic format of a search query. Basically, it prevents the model from just spitting out random gibberish when it first encounters a software tool.
But here's the catch, and this brilliantly illustrates why SFT fails on its own. SFT is all about memorizing fixed demonstration traces. It knows exactly how an expert solved a specific problem in the past, but it totally lacks the ability to teach the agent when to avoid bad calls, how to handle an unexpected error, or how to navigate trade-offs in dynamic, ever-changing environments. For that, the model desperately needs reinforcement learning, or RL, to optimize for cumulative returns through good old trial and error.
So the absolutely crucial point here is that imitation learning provides basic competence, not policy mastery. SFT is really just a warm start. To actually survive the real world, to know, say, when to stop researching, or to realize that a tool is totally broken and try another one, the agent absolutely needs the robust decision-making optimization of reinforcement learning.
Section 2. The tool calling trio.
Now, if you just throw an agent into an environment, it's going to flail around randomly. To fix this, researchers actually decompose tool usage into a three-part decision tree. First up, when to call a tool, like, is an external tool even necessary, or can I just answer the user directly? Second, which tool to call. Out of my whole arsenal, is a calculator, a weather API, or a web search the right choice here? And third, how to construct arguments. How do I properly format the specific JSON syntax to actually make this tool run? Separating these subskills, that's the real secret sauce. And by separating those three steps, we can neatly isolate the reward signals. If an agent calls the wrong tool but formats the syntax perfectly, we can reward the syntax but penalize the choice. This decomposed reward framework massively reduces the credit assignment difficulty, which is just a fancy way of saying the model knows exactly why a specific trajectory was good or bad, and that leads to highly controllable behavior.
Section 3. Rewarding and training agents. Now check out the asymmetry in these numbers, because it's super interesting. A correct final answer might get a massive plus 10 reward, while using the wrong tool only gets a tiny minus 0.3 penalty. We heavily reward success, but we only mildly penalize errors. Why do we do that? Well, because if the penalties are too harsh, the agent gets absolutely terrified of making a mistake and basically collapses into a degenerate strategy where it simply refuses to use tools at all. So asymmetry encourages exploration. With our rewards dialed in, we put the agent through a curriculum. Notice how complexity is introduced gradually here. We don't just dump the agent out onto the open web. No, we bootstrap with SFT. Then we spend whole epochs just teaching it when to use a tool, then which tool, then how to format it. It's only in stage 4 that we finally combine these into multi-step pipelines. This gradual scheduling ensures the policy truly internalizes tool usage instead of just blindly memorizing it.
Take a quick moment to think about what you should really take away from this. Why does this exact training pipeline matter to you? Because structured reinforcement learning is literally the mechanism that changes software from brittle, hard-coded scripts that completely break when a button moves into dynamic, self-improving workflows that adapt to actually get the job done. It is the very foundation of the autonomous software we're all going to be using tomorrow.
Section 4. Capability versus reliability.
Here we really have to contrast two fundamentally different metrics. Pass at K measures capability. Out of, say, 10 attempts, did the agent manage to solve the task at least once? It's kind of like asking if a golfer can hit a hole-in-one. Pass to the power of K, on the other hand, measures reliability. Can the agent solve the task consistently 10 times out of 10 repeated executions?
And this is where it gets real. When tested, a top-tier state-of-the-art agent hit an impressive 78% on capability. It could solve the vast majority of tasks eventually, but its reliability, its ability to solve those exact same tasks every single time without fail, only 36%. That proves a massive, massive disconnect. Can solve once is fundamentally different from can solve every time.
So why do agents drop the ball on repeated runs of the exact same task? The research points to three main culprits. First, stochasticity, which is just the natural randomness in decoding. Second, instruction ambiguity, where the prompt has multiple interpretations. And crucially, planning variability. Sometimes the agent just randomly chooses a really fragile strategy instead of a robust one. Like, it might try to use a super complex, multi-step search when a simple calculator query would have guaranteed success.
I really want to reiterate this to you. If you are building, buying, or implementing AI agents for your business, you absolutely must demand reliability over flashy one-off capabilities. In the real world, a 36% success rate on an automated accounting workflow, that's a total disaster. Deployability requires absolute reproducibility, for sure, not just one lucky rollout that makes for a great demo.
And finally, Section 5, Single versus Multi-Agent Systems. When we're designing these systems, we have a fundamental choice. Unified reasoning uses a single agent. It preserves the full context of the task natively, maintaining a continuous, uninterrupted internal train of thought. Distributed orchestration, on the flip side, uses a multi-agent system. It splits the task into planners, workers, and critics, which means externalizing communication through intermediate message passing.
Now, splitting up the work sounds awesome, right? Like a highly efficient team. But actually, it introduces what we call the coordination tax. Every single time these agents talk to each other, information gets compressed or even lost, creating massive bottlenecks and context fragmentation. Plus, your fixed token budget gets aggressively eaten up just by the agents coordinating with each other, rather than actually solving the problem at hand. And worst of all, if one agent makes a mistake, that error just propagates through the entire swarm.
Which brings us to this incredibly powerful punchline. Recent data actually shows that when the computing budget is normalized, meaning you give them the exact same amount of thinking tokens to spend, a single agent system often matches or entirely outperforms complex multi-agent swarms on reasoning tasks. It turns out, unified reasoning is incredibly strong.
So here's your actionable takeaway for system architecture. Your default design strategy should absolutely be to start with a single agent baseline. Keep it simple. Treat multi-agent systems as a deliberate escalation. Add more agents only when you genuinely hit a wall and specifically need parallel search to explore multiple paths at once, or you need highly specialized role verification. Otherwise, keep your reasoning unified.
All right, so we've covered the whole journey today, from simple imitation to the tool calling trio, through asymmetric rewards, and the harsh reality of single versus multi-agent designs. So I'll leave you with this provocative question to ponder. When you interact with or evaluate an AI agent tomorrow, will you settle for mere capability, or will you demand true, repeatable reliability? Thanks so much for joining me on this explainer, and I'll see you next time.